Welcome to our second probability video. Last time we found out how important a sample space was. That's a list of all the possible outcomes of an experiment. Once you have it, you can simply count the number of favorable outcomes out of the total outcomes for your probability. So let's look back to our tea box example from last time. We were choosing 2 tea bags of the following. We had 2 mint, 1 chamomile, and 1 pumpkin spice tea bag in a box. If we picked out 2 of those at a time, these were the possible choices. Let's suppose that I wanted to ask, what's the probability that I chose at least 1 mint tea bag? I can simply count 1, 2, 3, 4, 5 out of these 6 possibilities would give me at least 1 mint tea bag. So there's only one choice that didn't give me any mint tea bags. Or consider the 2 dice example where I rolled 2 dice, and so here was my sample space. What is the probability of choosing, or I should say rolling, 2 dice that are exactly the same number? You see that I have 1 1, 2 2, 3 3, 4 4, 5 5, and 6 6. So there are 6 possibilities out of the 36 choices, and so that probability would be 6 out of 36. Because I'm using fractions, I do want to convert to lowest terms, and so that's the same as a 1 in 6 chance, or a 1/6 probability. So there is another tool for figuring out the sample space called a probability tree diagram. Let's look at one of those. This is page 8 of your handouts. And so in the following experiment, we will roll 1 die and flip a chip that's red on one side and blue on the other. And so this would be our probability tree. You notice that there are a couple stages of our experiment. The first stage is rolling the die. And so I might get a 1, a 2, a 3, a 4, a 5, or a 6 in that first stage of my experiment. On the second stage, once I've rolled my die, now I'm going to toss that chip and see whether it lands on red or blue. So for each of these numbers, I could have a red or a blue come up on the chip. And so you see that once I make this tree, in my next column, I've simply listed the outcomes that I had by going along the tree branch. And so if I went and rolled a 1 and then got a red, that's listed here as 1 red. It looks like there are 12 different equally likely possibilities or outcomes for this experiment. So that would be 1/12 along each of the branches. And so, for example, if I wanted to know the probability of rolling a 6 and landing on a red, I would say, okay, here's a 6, there's a red, so it would be this one right here, and that has a probability of 1 out of 12. I could have also figured that out without actually using the tree diagram. I could simply say, okay, let's use that fundamental counting principle. What's the probability on each step of this multi-stage experiment? On the first stage, I have a 1 in 6 chance of rolling a 6. And then on the second stage, I have a 1 in 2 chance of getting a red. And so when I multiply those 2 probabilities, I would get 1/12. Remember that in math, when we say and, that means to multiply. And so let's look at a second example of a probability tree diagram. So now we have a family that has 4 children, and so we want to know what's the probability of having a girl, then a boy, a girl, and then a boy. And so one of the things that we're assuming is that it's equally likely to have a boy or a girl. And so on each step, the probability is 1/2. So again, my first stage, I could have a girl or a boy. My second stage, I could have a girl or a boy. My third stage, I could have a girl or a boy. on each of these. So this is how you draw your probability tree. And then on the fourth stage, I could again have a girl or a boy. And so what is the probability that I have what I wanted, a girl, boy, girl, boy? So if I go along my tree, I can figure that out. Girl, boy, girl, boy. So that would be this choice. And there are 16 different equally likely possibilities. And so the probability of getting that particular order of children is 1/16. Now you might say, again, I don't need to draw the probability tree to figure this out. You don't. You would just do 1/2 times 1/2 times 1/2 times 1/2. And you notice that the probabilities are the same for girl and boy. So this is the same probability for any different combination. When this really becomes an important tool is when you're asking a more complicated question, such as, what's the probability that at least 2 of the children are girls? And so then I would go and I could use my tree to count how many have at least 2 girls. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It looks like 11 out of the 16 choices have at least 2 girls, and so that would be that probability.